All right, good morning. Welcome back to Calculus 2. So we're going to talk about work problems today. Uh, this one is a spring problem. This is like the nice one to go ahead and deal with. We have a force of 18 pounds is required to hold a spring stretched 8 inches beyond its normal length, its natural length. How much work, W, is done in stretching it from its natural length to a length of 11 inches beyond its natural length? So this is really a two-part problem. There's an algebra part and there's a calculus part. So the first thing we're going to do is we're going to write down Hooke's law, F is equal to KX. For the people in engineering, you will use this for just about everything. There's more advanced forms of it where the pieces of it get to be bigger and bigger and bigger, but this is a very, very fundamental kind of an idea for everything that you're going to, well, for a lot of things that you're going to do. Okay, so we have F equals KX, and what we're going to do is we're going to take the piece of information we know. We know that 18 pounds is required to hold the spring 8 inches beyond its length. First thing I'm going to do is we usually work in foot pounds, not foot inch or pound inches. So I'm going to make this into, I'm going to change this to inches to feet instead so we can go ahead and work it that way. Okay, so the first thing to do is we're going to say we have 18. That's my force is equal to K, and then we're stretching it 8 inches. So I'm going to say that 8 inches is 8/12 of a foot. Okay, and we can go ahead and reduce here. We can say, okay, 18 equals 8/12 reduces to 2/3. So we're going to say this is going to be 2/3 K. Solving for K, we have K is equal to 18 times 3 over 2. Go ahead and cancel some stuff. We have K is equal to 27. So my spring constant for this spring is 27. Okay, so going into my spring equation here, this would be F is equal to 27x, right? So that's what we have there. So what we're going to do now is we're going to go ahead and calculate the work. And work is equal to force. And if it's a variable force, in this case it is, we need an integral. So we're going to go integral from its natural length, which is, we're going to set that to be 0, to 11/12 of a foot because we're stretching it 8 inches. So we have force is equal to kx. So instead of this, the force times distance, which is going to be our dx. So we're going to say, okay, replace our force. That was equal to 27x. So we have W is equal to 27x dx. And of course, we're going to put that in an integral between 0 and 11/12. And we'll go ahead and calculate our answer here. So first thing I'm going to do is take that 27 out. Okay, 0 to 11/12 of x dx, and we end up with 27 times x squared over 2 as x ranges from 0 to 11/12. Okay, so we can go ahead and plug that in there. So plugging that in, we end up with, let's see, we have 27 over 2, plugging in by 11/12, so 11 over 12 squared minus 0. That's nice for a lot of these problems. So we actually end up with 27 over 2 times 121 over 144. And we're going to get an answer of 363 over 32 foot-pounds. Okay, and that would be our answer. All right. Now, those are pretty nice warm-up problems, and it'd be nice to see one of those. Okay, like it's a nice problem. It's like, yeah, I can get this one right. So that's always nice to deal with. I'm going to go ahead and pause this for a moment and go ahead and write down the next problem. Okay, the next problem we have here is we have this tank that's full of water. We're going to calculate the work needed to pump the water out of this spout that is 1 meter over the tank. Okay, and then I've gone ahead and give us a drawing of the system here. So it's a poor drawing, but this is triangular. If you take a prism and like turn it upside down, just assume there's supports or something that it's not going to fall over. Okay, or it's in a carrier, it's in a container that actually allows this thing to sit. And our job is to figure out how much work is needed to pump the water out of the tank here as we're going to go ahead and figure this out. Okay, so the idea here is, again, we need work is equal to force times distance. And we're going to see if we're probably going to have to integrate this because something in here is going to be is going to be changing. Now, the force, we're going to say that the force is equal to the density. We're going to use, that's a rho, okay, times volume. Just to do the unit analysis on it, we're going to say the density is in this case, we use meters. So we're going to say we have kilograms per meters cubed. And of course, our volume is going to be meters cubed. So we're going to have to multiply by G, right? Meters per second squared for the acceleration due to gravity here. So this is going to be a kilograms times force of gravity. So it's going to be meters per second squared. And this is going to go ahead and give us our newtons, and that's going to be our force. Okay. So we can go ahead and do that. So a thing you're going to have to need to know is that the density of water, okay, so rho for water is going to be 1,000 kilograms per meters cubed. Okay. I know that I was like, wait a minute, I thought it was one. Like that's grams per centimeter. So this is a little bit different because we have the units given to us as kilograms and meters cubed. This would be given to you in the problem. You don't have to memorize this. If it's going to be in American units, freedom units, it's going to be in pounds per square foot or cubic foot rather. Okay. I wish the world would go, I wish we would join the world and go to metric, but that's a different rate for a different time. Okay, so I have my little tub here. Okay, it's got a height of 4 feet. It's not measuring this diagonal, it's the height here. It's supposed to be 4 feet. The spout is 1 meter above it, and then our width, of course, is going to be 4. First thing I'm going to do is draw a little triangle so I can get a cross-sectional area, because the idea here is we want to figure out the volume of what's going on, and then we'll go ahead and figure out what's happening with this. So because this is not a constant volume, depending on where the water level is, it's going to change. So one of the things I want to do is come up with some kind of an expression for what's going on here. And we're going to go ahead and we're going to say y is equal to rise over run. That's going to be, well, I'm going up 4 units, 4 feet, or 4 meters, divided by 2 meters for my rise over run, x. I started at the 0 point, so just looking at lines for that way, we know that y is equal to kx, and we have, or mx rather, we just have to figure out what the slope is. So we have y is equal to 2x, or x is equal to y over 2. Okay, so we can go ahead and figure it out that way. All right, now, as I'm going through and setting up my integral here, we're going to say we have this. We have our integral, and we're going to pump out the whole bits of water. So the whole volume of water is going to go from 0 to 4. But wait a minute, we have one more meter to go. So my distance, so as I'm looking for force times distance here, my distance is going to be 5 minus, we'll say we use y. Okay, so 5 minus y as we're doing this. Okay, and now what we have to do is we have to come up with our volume equation. The length of this thing, I didn't write this down, is going to be 6 meters long as a tank. Okay, so that, again, that would be given to you. So my length is going to be 6, so I'll go ahead and type that in. And now what I have to do is I need this face here. So we're going to have, let's see, I need 1/2 base times height. So we're going to say base is going to be, we need, actually, when I go ahead and do this, right, we have 2 of these y over 2's here. So we're going to say we need 2 y over 2's as this part here happens. And that's going to go ahead and figure out my my little piece here. And then, of course, the thickness of this thing is going to be dy. Okay, because we can go ahead and say, okay, I need a little dy, and here's what's going on. Okay. And I think that sets up our integral pretty well here. Right? So we can go ahead and figure this out. If I have my camera on, you can see the fact that my cats are swarming me because it's past their breakfast time and they are very insistent on eating the cat. Okay, so let's go ahead and look at that. Okay, for a moment, I'll go ahead and do that. Let's see. We need to do this. I don't know what we're doing. Okay, let's go ahead and sort this out. The 2's conveniently cancel. So here we have, let's see, we have let's pull out what we can pull out. So let's see, we have, oh, I need a y in here for my height. So let's go ahead and make sure we have a y in here for my height. Okay, so we're going to be able to do that. So let's see here. We have our, go ahead and figure this thing out. So we have our density, okay, which is going to be times G. So we have 9.8 times 1,000, right? That's my density of water. And then we'll have our integral from 0 to 4, and we'll go ahead and figure out what we have left here. So it looks like we have a 6 times, let's see here. How did I do this? We have our, there we go. We have our 5 minus y times our 6y dy. And that is our bit of calculus that we're trying to figure out here. Okay, so we have 98,000 out here, 9,800 rather. Yep, 10.8 times that, so we have that. And then we're going to say we need integral going from 0 to 4. Here we have 30y, 5 times 6, minus 6y squared. Why didn't I pull the 6 out? I could have. I just didn't want to multiply this by another 6. And we have our dy, and we'll go ahead and figure out what's going on here. All right, so we can go ahead and integrate now. So let's see, we're going to have 800, and we're going to have 30 over 2 y squared, the y squared over 2, minus 6y cubed over 3, going from 0 to 4. The important part is remembering that 5 minus y, because we have to push it out 5 units, and we're going to be dealing with all of that. Okay, so here we go. We have, how did they do this? Instead, this was 9.8 times 10 to the third. That's probably a better way to say it. And let's go ahead and deal with this. So we've got 15 times 4 squared minus 6 over 3 is going to be 2 times 4 cubed. Okay, so we'll go ahead and sort that out. Let's see. I go to my calculator here. We have 15 times my 4 squared, okay, is going to be 240, minus, and then we have 2 times 64, so we have 2 times 4 cubed equals, and that's going to be 128 sitting over there. Okay, this again is all times 9.8 times 10 to the third. So we can go ahead and sort that out. So we can say, okay, we got 240. Let's go for this 240 minus 128 is 112. And then we have times 9.8 times 10 to the third. Okay, so we go ahead and type that in. So times 9.8. Second function. Where's my EE button here? There it is. That means times 10 too. There's 3 different E's on this calculator. The second function, comma, is the one that gives us the right answer, the right value for this thing. So that gives us 1097. Okay. So let's see. I lost it. Okay, so that's how you do a problem like that. There's a lot of examples on YouTube that probably do a better job than I did. 976,97600. And this is going to be in joules. Okay, so getting this problem out to come out, the important thing is making a relationship in this triangle, getting the volume of the triangle. So I should have said that we have a y going down here. So going up, we have y. Okay, and then getting that relationship, turning everything into y's, and then realizing this distance that we're raising the water to is 5 minus the little slice of water that we have. Okay, and that's kind of the important part for them. I'm going to say thank you very much for watching the video. Take care, and I'll see you in the next video.